So this video shows how you can check whether your data is kind of suitable for the thermobarometry model you have chosen. And this is really, really important. If you're using models outside of their calibration range, your results are probably going to be a load of rubbish. So as normal, we go to Thermobar read the docs. You're going to scroll down to other functions, assessing the calibration range. Click here to download, and there's a separate video showing how to do this. And put these two files somewhere in your computer where you can find them easily in whatever Python program you use. So I am using JupyterLab. So you can see this is the Jupyter notebook I downloaded. And then you can see this is the sort of example file which has the data in it. So we can just look at that quickly. This basically has tabs for different phases. This is sort of all of the phase data you might have from a new volcanic system you're working in. So to start with, we're going to import Thermobar, and you need to uncomment this if you haven't installed Thermobar yet. Okay, so first we're going to load in sort of all of these compositions. So we use the pt import Excel. So basically we're telling Thermobar the file name and the sheet name here because we're getting liquids. And then this will return all columns. We just need to do one extra step to get out the liquid compositions. Same for pyroxene, tell it where your pyroxenes are saved. Same for amphibole, tell it where your amphiboles are saved, and you can run that. Now Thermobar has embedded in it the calibration data sets for a number of different models, basically all of the ones where I could find the original calibration data. So there's basically two functions, so pt generic calibration plot, and this will basically tell you what models are available for the different phases. And it tells you kind of how to use it, but I'm just going to talk you through this. So first, let's use amphibole. So the first thing we have to tell the function is a data frame with our mineral compositions. So here we called it amps1 when we loaded it in. So we're going to tell it that. Say we want to use the amphibole only barometer of U and Much. So we specify Much 2016 as the model. And then the final things we have to specify are what we want to plot. So in this case, I am plotting the magnesium number using iron total in the amphibole versus the aluminum content of the amphibole. What this will do is it will underlay the calibration data, so this is the white circles, and our data. And you can see I probably wouldn't use this barometer for these samples because they are much, much more primitive and offset from the trend of the data used for calibration. You can also sort of change how this works. So you can say, let's set sort of the opacity of the calibration data to 1 and our data to 0.8, or you could put this much, much lower if your data is sort of like overlapping with the calibration. So you could set this at 0.1. So this just gives you a little bit of flexibility of how you plot it. And you can also specify the order you want to plot the data in. So here we're saying put the calibration data on the bottom. So now you can see our data is overlain on top. So this custom plot just allows you to really, really quickly look at different chemical parameters and assess whether you're working within a calibration data set. If you want to make more complex plots, you can use this function, return cali dataset, and you just give it the model name. And that will return basically all of the data you might need for other plotting. So we can run this quick and we can just have a look. So we take the name of the variable and we type head. So you can see this is kind of all of the data that you might want to plot for the Much model. So here we're going to plot using matplotlib now, so we're not using custom plotting, we're using sort of Python's plotting thing. We're making a two side-by-side subplot, and on the first panel, AX1, we're plotting sodium against magnesium in the amphibole. And on the second plot, we are kind of doing that, but now instead of using Much, so the left-hand one uses Much, the right-hand one uses the Rodolphi 2021 dataset. So what you can see when you plot these is that basically our data is not within the Much calibration dataset, so we really don't want to use this model. Whereas to an extent, a vast majority of it is within the calibration dataset of Rodolphi. So this is obviously looking at composition. What we might also want to do is see whether our calculated pressures and temperatures lie within the calibration range. So here we're using the thermobar function to calculate amphibole only pressure, and we're feeding it the amphibole compositions, and we're telling it we want P Much 2016. And then we're doing the same for Rodolphi, but because the temperature is pressure dependent, we are using the iterative function. So calc amp only pressure temperature, give it the amphibole compositions, and give it an equation for pressure and temperature. We could then use the generic calibration dataset, but instead now of, we're basically telling it that we want X of the calibration data to be P kilobar, Y the magnesium number, and then we're feeding it sort of the pressure that we've calculated. So in this case, this is P Rodolphi, P kilobar calc, which is the output from this calculation. You can see that here. So basically we want this column and we want to feed this in for our data. And this basically, the reason this is a separate input is so that this can be in any format. So it just makes your life a bit more flexible. So now you can see in terms of pressure, magnesium number space, our calculated pressures are still within range. We might also want to plot pressure against temperature. So again, this is how you plot the calibration data, so that's how they're stored. And then for your data, you just specify sort of the data frame, which has the calculated variables in. You can see you're kind of in range, you're possibly a little bit hotter than the calibration array, but this kind of gives you a way to visualize, you're not miles away from it. We can do the same for Much. So again, specifying what we want in the calibration data set and then our calculated pressure here. And again, we're really not in the calibration range. Okay, so that's amphibole. For CPX, we have a lot more models which are covering a much wider range of sort of pressure temperature composition space. So here we are just getting the calibration data sets for Cara Brugman, Maurizio Petrelli, David Neve, and Masotta here. So these are 4 models that we have. And then we basically want to calculate perhaps the CPX components. Maybe we want to see how our J-light content compares to what is used in these models. So for our measured CPXs, we've loaded in Excel. We are just going to say input CPX comps and use the calculate calibration components function and tell it these CPX compositions. So I can run this and you can just see that this basically returns all of our data, but then returns all of these other parameters you might be interested in for CPX. Sorry, I just deleted a cell. Okay, so let's try not to delete cells we need. So now we might want to plot on sort of a subplot side by side again, the magnesium number of the CPX in the Masotta calibration dataset versus the sodium plus the potassium of the liquid. So for these CPX datasets, not only do we have the climate pyroxene composition, we also have the composition of the liquid that the experiment was done in, which really helps us assess our calibration range a bit better. So we're doing that sort of for the calibration datasets to start with. So here we are specifying the column names sort of in the plotting functions itself. What you can also do is you could specify at the top what columns you want. So here we want temperature and pressure, and then you can just write X2 and Y2 in here. This allows you to change it a little bit easier. So these are just 2 different plotting styles. Regardless, and we can sort of visualize here what sort of the calibration data sets of these different models are, even before we start looking at our data to see how it compares. Or we can plot our data amongst sort of the calibration range of a given model. So this is plotting our data sort of amongst the calibration range of David Neve. And you can see our data in red extends to much lower magnesium numbers and sort of is not really in the calibration range. You could at any point calculate pressures and temperatures like we did for amphibole. So here we're calculating CPX only, pressures and temperatures using the Petrelli machine learning algorithm. And then we can plot sort of the calculated pressures and temperatures in amongst the pressure and temperatures of the calibration data set. So that can be useful. You could even do this for CPX liquid melt matching. So here we're going to take our inputted CPXs, our inputted liquids, and do melt matching on them. So this is something people commonly do. And then we're going to plot up the 4 calibration data sets again, but now we are going to add in the composition of all of these matches on top as sort of these clusters. So you can change the opacity on these. You obviously do not really want to be using the Brugman thermometer here, so this can just help you visualize it, or you can plot it on a small diagram as well. So there's just a few more examples of plots you can make, but these functions are highly customizable. You can get that calibration data set, you can make any plots you want, and I highly encourage you, anytime you're doing thermobrometry, to plot not only your mineral compositions, but also your calculated pressure and temperatures within the range of pressures and temperatures in the model that we use for calibration.